About kinetic molecular theory, and there's a couple applications on here, or thoughts more than anything else, at the top of your sheet there. Number one, it says particles are so small compared with the distances between them that the volumes of the individual particles are ignored. And these are just some statements. You're not ever going to have to recall these. So when we talk about kinetic molecular theory, we're talking about how gases behave and what we can do with those. And when we talk about solids and liquids, we'll talk about those aspects of how they move next to each other or vibrate next to each other. Number two, the particles are in constant motion. The collisions of the particles within the walls of the container are the cause for the pressure exerted by the gas. So in other words, as a gas particle flies by your face, what pressure does it have? Does it have any pressure? It does not have any pressure until it actually strikes something. Okay, so there's no way that we can say that that has any pressure until it makes an impact. So that's what that statement's saying. Number three, the particles are assumed to exert no force on each other. They are assumed neither to attract nor repel each other. So when we talk about that, typically we're not going to have gases flying around each other and then clump up and drop down to the ground. Okay, so that's what that's saying. And again, just a good theory. Number four, the average kinetic energy of the collisions of gas particles are assumed to be directly proportional to the Kelvin temperature of the gas. So when we talk about average kinetic energy, we're also talking about temperature. So that's how we measure average kinetic energy. You may see a question that says, determine the average kinetic energy for a system. And there's a couple ways we can do that. We'll actually do that here shortly. Actually, very shortly. Number one, says calculate the average kinetic energy of SO2 molecules in a sample of SO2 gas at 295 Kelvin and 733 Kelvin. Looking at your periodic table, I'm sorry, not your periodic table, your equation sheet, still in the gases, liquids, and solutions, this equation is right above the R1 divided by R2. We'll actually use that a little bit later on. I don't know if we do that one today or not. That may be tomorrow. But you can see it on your sheet where that's located at. And let me identify the variables here. It says 3/2 RT. The 3/2 is just a fraction. And then the R that we will be using will not be the 0.08. Since we're looking for energy, the R value that we will use is the 8.31, and that is joules per mole Kelvin. Okay, so it's a little bit different, and that R constant is also located on your equation. For the SO2 molecules, let's go ahead and do 3/2, and it's 8.31 joule per mole Kelvin. And the temperature is at 295. We'll leave it in Kelvin since we have our unit as Kelvin here, so 295. Let's get a value there. Calculator's over here. So 3,000, actually put 3.6, we'll say 8, times 10 to the 3, and what's my unit on that? Joules per mole, good. Okay. The second part of that question says at 733, so we'll do that. So 9,100, we'll say 14. So, okay. Did everybody get those? Try number 2 on your own. Don't look up here. Number 2 says calculate the average kinetic energy of chlorine molecules in a sample of chlorine gas at 295 and 733 Kelvin. What's the matter? They're the same thing. Very good. So the thing here, or the point that I want to make sure that everybody sees, it doesn't matter what the compound is, or what the molecule, or what the atom is. If it's at this temperature, that is the average kinetic energy. Okay? Now, does that mean that if I'm looking, what did I have? SO2 and chlorine. Okay. The calculations I did here were for the sulfur dioxide, and then I had you do the chlorine. Do these weigh the same? I think this is about 70, that's about 60 some. They don't weigh the same. So, do these move at the same speed? No. But they have the same impact, okay? So in other words, which one was heavier? I think it was this one is a little bit heavier. It moves slower, but it still has the same pressure. This one moves a little faster to have the same pressure. Okay, so doesn't matter what we're looking at. That's why there was nothing molar mass wise included on this. So it doesn't matter what the thing is. This is its average kinetic energy at this temperature. Okay, that wasn't meant to be mean. I was just checking to see how long it would take you guys to figure that out. All right, number 3. I don't think you guys, or I hope you didn't do this in general chem. Shouldn't have. This is root mean square velocity, and the equation for this is located right above. We won't ever do the Ke per molecule, but we'll do the Ke per mole. That's what we just worked on here a moment ago. The equation that we have here, and the one that we'll use, is the 3RT. The 3RT with the big M. Okay, and that is our root mean square. I don't know why they use a U there. That has always mystified me, but I don't care. So let's identify a couple things here. The R is still our 8.31 joule per mole. Kelvin, sorry. Our temperature, still a Kelvin. But here's our difference. What does the big M represent here? Molar mass. So again, the molar mass is typically in what unit? Grams per mole. However, we can't go with grams per mole with this molar mass. And does anybody know why? What's that? We have to use kilograms, but why do we have to use kilograms per mole? Does anybody have any idea as to why? What do you mean? Go on. Go on. Still waiting. What unit do we need to change? It's in joules per mole Kelvin. There we go. We have to look at the joule here, which is a conversion, which is not on your equation sheet, and I don't know why. That's probably the most frustrating thing. But a joule is a kilogram meter squared per second squared. Okay? That's the unit. If you've had physics, that'll be familiar to you. If not, what's that? Yeah. Kilojoules meter squared over second squared. Okay? And it's interesting, but hey, that's what a joule is. So I will give that to you anytime that this type of question has appeared on the AP exam. That has been given to you. So you don't have to memorize that, but it's odd that they don't put it on the equation sheet. But there's a lot of odd things that go on this test. All right, so that's why the molar mass must be in kilojoules per mole, so we can cancel out our kilojoules. And then what else is interesting about this? We have meters squared per second squared. Why do we think we have a square root or a radical on there? So we can reduce it down to meters per second, which will be speed. Isn't that cool? It all works out, even in the chaos and craziness. So let's work out number 3. Let's erase all that garbage. All right, so number 3 says, calculate the root mean square velocity for the atoms of a sample of argon gas at 35 degrees Celsius. Okay, so we don't have to do anything to the 3, obviously. the 8.31, and that's joule. And I'm going to write it out like this, and then I'll do some conversions here. So I want you to see what I'm doing here. Okay, so again, 3.
Where are you getting that 3?
It's 3 RT.
Oh, okay, I see.
3 RT big N. Okay, so that's joule per mole Kelvin. And then the temperature they said was 35, so what is it? 308. Okay. And the molar mass, it's argon, so what is the molar mass that we'll use here? Not 39.95 grams per mole. And if you need to do this, that's fine. Convert it to that, which is now, I believe, 0. Ooh, not too many. Or was that right? 0? Is that correct, or do I need to type that in on my calculator? You guys want to make me calculate? I think you're by 1,000. All right. It's early in the morning. I want to make sure. So 0.03995, and that's kilograms. And again, don't have more than one divisor. Put that mole right there. Okay. And of course, it's all under the radical. I am going to now change the units for the joule to this, to kilograms meters squared per second squared. Okay. And then put the 308 back in there. So I'm just doing a conversion here. And you don't have to do that. You can go directly to kilograms. Oops, I forgot to. No, I didn't. You can go directly from joules, if you know that, kilograms to meters squared over second squared. Mole Kelvin, still down here because it's part of our, and then the 0.03995 kilograms. All under the radical. All right, so let's look at some things we can cancel out. Moles, get out of here. Kelvin, gone. Kilograms, gone. So we're left with meters squared over seconds squared. Now let's get a value here. Okay. So 3 times 8.31. Oops. Divided by. Okay, so my calculator at this moment says 192,201 da 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 da. Okay, I don't want to rewrite that. So put that under the radical. What happens to my units when I take the square root of that unit? Goes from meter squared per second squared to just meters per second. Okay, and then square root the answer. And I get 438. Now that's just a little bit faster than I can run. Okay. God, you guys are bad. I didn't even know what a 400 meter never mind. So yes, gas particles move pretty quickly here. All right. So again, when working this problem out, if you need to show the joule, that's fine. But I must see the kilograms per meter squared divided by second squared. Okay? We don't go from joules to meter squared. Don't do that. So if you're looking for the minimum, and I know you guys are all about efficiency here, this is the minimum I need to see. Okay? Yes, I know that will appear in your calculator. You can take the radical of that. Some of you even have calculators where you can type the radical in and then da-da-da-da. And it's not a graphing calculator. Because Casio, superior Japanese technology. All right, so. All right, questions on that? Let's see here. Number 4. Try that one on your own. Try that one on your own. Don't peek up here. Yeah. I'm missing a 0? Where?
Kilograms per mole. 0.6406.
Oh, thank you. That's why, guys. That's why I have my spotters here. That's good. Can't do math in my head. That's a problem. 295. And mole mass. And when you get done, you can start on the homework. Nice light day today. Any questions on the 295? Plug and chug, right? Pretty straightforward, I hope. And as the temperature goes up, it does make sense that the particles are going to go faster. Okay, so, and think about it. At 0 Kelvin, how fast should this thing be moving? Not at all. So if we place a 0 right there, well, that does some really crazy things, but it's not going to move. Okay. So again, for you minimalists out there, this would be the minimum, and this would be the minimum. Okay. And I will always show on the board here all the steps possible.